sort of familiar to you. Have you looked at these before? Some yes, no. I'm wondering, yeah, you all have you?
Yeah.
Okay.
Look, I remember them.
So, a sine graph. So, what we could do is I could get you to type into your calculator sine 15, sine 30, sine 45, blah, 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 and get you to plot those points. Very tedious, very dull. If you had done that, you would end up with this shape. Now, you will see that it keeps going on and on and on and on. Okay? Does anyone remember what the oh, you can see from the diagram. What's the maximum value that it always gets to? 1, and then the lowest number it ever gets to is -1. Okay? You probably want to remember these intervals. 90, 180, 270, 360. They're your benchmarks, and that's how I would always sketch one of these diagrams. Now, the way I teach stuff later on solving trig functions is to sketch a diagram. So I'm hoping that you're going to get very familiar and confident with these sketches. As I say, you just want these points, 90, 180, 270, 360. The sine curve makes an S through the y-axis, okay? So it goes through 0, 0, and it kind of makes an S shape. So if you were to sketch this, I would always sketch 0, 90 and 1, 180 and 0, 270, -1, 360, 0, and that's probably enough. And then you know it goes, so you would then just be able to draw that. Okay? Good? Good, yeah. Terminology, a period. That means how long does it take, or how many degrees does it take to go through one cycle. So hopefully you can all see if it starts here, it would finish here, so that would be 360 degrees. Now, we could have labeled this -290 and this would be 450, okay? So you didn't have to start at 0 and end up at 360. You could have started here at -90 and ended up at 270, but it still would have been 360 degrees, yes? So how long does it take to go through one cycle? And as long as you're finding corresponding points of the yeah, that's very technological word. Okay. You have to spell it correctly when you describe that.
So like one hump?
Well, one hump up and one hump down.
One has a blue?
The green.
Oh, so like wow, it's 2 points in that distance. That's what I thought you meant. Where you put these two.
Well, that would be the same distance because that was a down, up, down. It just keeps going, wading up and down. You with me? So what I'm trying to indicate is it doesn't actually matter. You don't have to start there and go. You can start here and go. Okay. So that's your period, 360. The amplitude. Do we know these words?
Yes.
Oh, yeah. Why am I going so slowly then? Shut up, Miss Harrison. I don't know physics. Does everyone do physics?
No.
We've all got it. So the amplitude. Now I like to call this my central line. Okay, because my wave goes up and down through that. Okay, but not everyone calls it central line. They might do, I don't know. But that's my central line. So the amplitude is the distance from that central line to the top, or from that central line to the bottom. Okay. In this case, it would be 1. Now, sometimes, especially when they start moving these graphs, people get a bit confused and they don't really know how to find this. So another way of finding the amplitude is to say it's half the distance from top to bottom. So my very top is up here, my very bottom is down here. Yes? So half of that distance, so that's a measurement of 2, so half of that is 1. Okay, that's my sine curve. Cosine curve. Funnily enough, similar shape. Same intervals, 90, 180, 270, 360. This one also goes up to 1 and down to -1. This one, however, when we look at the y-axis, makes a C shape through the y-axis. Okay? So that's how I would suggest remembering them. You can remember them in any way you wish. So this one makes a C shape. Period, again, how long does it take to do one cycle? So if I take my 2 peak points, it's 360 degrees again.
What is the degrees?
Well, that's a very interesting point because maybe you're a little bit of a mind reader. Oh God, no, don't say that because now you're going to tell me you are. So, these graphs currently. Do you need spectacles?
Yeah.
Or is that just you're just trying to look into my head? So I've labelled these in degrees. We also have a measure of angles called a radian, which we will come to later on. We haven't done that yet, no. So we'll talk about radians later on, but radians are also trig, are related to trig graphs too. But for now we'll just talk about degrees. Oh God, look at that. She's scared me. Amplitude for this one, reads the same description between the top, halfway between the top and bottom, and again it's 1. So the sine and cosine curve are very similar. They are actually just translations of each other. So it is. So this graph here could be shifted left or right to give us the cosine curve. Tan. Tan is a little bit on his own, listen. Tan is not considered as much as sine and cosine. Okay, so we don't have as many questions about tan graph, but obviously he exists, so we need to think about it. Now, a tan graph should have these bad boys. Yes. Okay, did I write it down anyway? Yes, there are asymptotes at x is 90, 270, and so on. Okay, so these are asymptotes. So, remember asymptotes, we would show them with our dotted lines. And if you tried to type into your calculator tan 90, your calculator would come back saying it was an error because there is no value for tan of 90. Okay, so if you did tan of 89.999, it would give you a value, or 90.1 or 90.0004, and it would give you a value, but not actually at 90. Okay, and so the tan graph looks a bit squiggly. The period, so hopefully you can see how it repeats though. How long does it take to complete one cycle here? 180, yes. So because we're going from essentially -90 to 90, so our period is 180. I think about 90 there. Amplitude. Do we see the maximum point or the minimum point? On this graph it would be, but secretly there is no amplitude.
Oh. It's infinity?
Because it just keeps on going on and on and on forever. Okay, so you would never be asked about the amplitude for a tan graph. Okay, just the sine and cos. And so the reason that we generally look at sine and cos graph is because there's more information for them. There's more to them than there is than the log tan. Okay? Now, we've looked at transformations of graphs. Okay, those transformations of graphs apply to these graphs as well. So let's just think about how it might affect it. What did we say would happen if there was a number in front of a function? Do you remember?
It will move it.
Remember, not a number in front of. So a number in front of it. Stretch it. How would it stretch it?
Increase the y value?
Yes, it would increase the y values. Yes, so it would draw it that way. Okay? And so if we think about it, if we're increasing the number here, so let's say this said 3 sine x, we would be increasing the y values. So what is going to be affected?
The amplitude.
The amplitude, yes?
Mm-hmm.
It is on 4. And it's both of the values, so the whole thing is stretched this way. So, a can be any integer. We don't normally have not integers. Oh, it can be any value, really, I guess. I should have perhaps used, if I need to realize I shouldn't use the word integer. Generally,
I don't understand why.
sorry, why because what is an integer?
Like a number.
But what type of
Positive.
number?
No.
A whole number.
Oh.
But equally, you can have like 2.7. We don't normally, but so I shouldn't use the word integer. It's naughty.
Those counting.
It can be any number. Okay, so you can have anything in front of it. So, and what effect does it have? It's going to change the amplitude. So, whereas our amplitude initially was 1, whatever number is here is now going to be your amplitude. Okay? All right. So, this one here, first of all, we need to establish, well, are we looking at a sine or a cosine graph?
That's cosine.
Okay.
It could be y.
Yeah, so I hope it's not confusing. What I've done, I put the black one on as the original, okay, and then I put a blue one on that we're looking at. So the black original is just our sine x graph. Okay, so if we were looking at our blue one, we can see that actually now it's going up to 2 and down to -2, which means that my amplitude is now 2 rather than just 1. And so this must be y equals 2 sine x. So it's a situation where they may ask you to sketch the graph, giving you the equation, or give you the graph itself and ask to sit, and you need to identify the equation of it. So the things that you're looking for are, what is my amplitude? Okay, so remember, you get that from the half of the way the distance between top and bottom, or identify where your central line is and the measurement from that up or down. Okay? And this baby here, is it a sine or cosine graph first? Okay, so this one's cos, because it makes the c go through the y-axis. Where does this one go up to and down to? 3. Yeah, I can actually label it. It's really rubbish. Except my faults. So my new amplitude is 3. Oh. And so my graph must be y equals 3 cos x. Not too shabby. Alright, so that's just a number circle front. Oh. We could have a number circle on the ends. Who said this one first? Leon. Huh? No, I didn't do. No, I think someone started saying, and I was like, so if you've got a number stuck on the end, was it?
Right?
If it's number stuck on the end, moves up or down.
Which one is
That's when it's
in the bracket?
yes, in the brackets it's left and right. Yeah.
Okay.
Okay. So when you've got a number stuck on the end, that's when the whole graph translates. Okay, remember that word when you pick it up and shift it up or down. So it would shift up or down depending on what value we have stuck on the end. So as I've said here, this changes the position of the graph on the y-axis. It moves up or down by b units. And you can find that central line by seeing where the top of the graph is and where the bottom of the graph is, and dividing those numbers, adding those two up and dividing by 2. That will tell you where your new central line is. Okay? Because if you think about the sine or cosine graph, the maximum was 1 and the minimum was -1. So if we do 1 plus -1 divided by 2, you get 0. And that's why for the original graphs, the central line was at 0. Sorry, did I do that too fast?
No, but
So then we can find out where our central line is. So if our original central line was at 0, then if our new central line is at 4, it means it's shifted up 4 units.
Okay.
Does that make sense?
Yeah.
Or might not really?
That
I don't understand.
Alright, okay, so let's look at this one here. So the black one is my original. Okay, is that sine or cos? Cos, okay. So my original central line is here at 0. Yeah? And so if we establish where our new central line is, because sometimes it's easier to find where the central line is rather than anything else. You could look at this point here and say, well, how many units has that moved up? Like that's definitely an option. But you also may like to use this point here as your point of reference. So to find this value, what you would do is say, okay, my maximum value here is 2, and my minimum value is 0. So you would say 2 plus 0 and divide it by 2. That gives me a value of 1, which means that my new central line is here at the value 1. Which means that the graph must have shifted up by 1 unit. Yeah? Lots of these. So my new central line is at positive 1, which means this must be y equals cos x plus 1. So the main reason I'm suggesting to check where the central line is rather than just say, okay, well this graph just shifted up, is because sometimes they'll change the amplitude and the central line. So you can't just say, okay, well this was 1, this is now 2, therefore it must have shifted up. Because if they change the amplitude as well, then you're going to have different information. Okay? So try and always find where this new central line is. So find the maximum point, the minimum point, add them up and divide by 2. This one? So what graph is it originally? What's the black one? Fine, good, we're getting better at recognizing them. So let's find our central line. It's easy. So our maximum point here is -2. Our minimum point is at -4. So we're going to do -2 plus -4 and divide that by 2. -2 plus -4 is -6. Yeah. And -6 divided by 2 is -3. So our new central line is down here at -3, which means that this graph would be y equals sine x, take away. Alright, okay, so this one here is where you've got a value attached to the x before you apply the function. So it was one of those f of 3x, for example. Yes? So you've changed this one. Do you remember what happens when we have the number inside the bracket?
The graph.
Yeah, what would happen to the graph? It does stretch this way, but remember it's a little bit different in that it doesn't actually go the same, it doesn't stretch the same way. It would actually be stretched by a scale factor of 1/3.
Oh yeah.
Do you remember that?
Yeah.
So when the number is in here, it doesn't make it go further away, it actually makes it go narrower. Okay? So the easiest thing to identify here is that because that's affecting how quickly something is happening on the x-axis, it means it's changing the period of the graph.
So if I was to have a minus 2 in there, would that make it?
Alright, so the minus, remember the minus inside the bracket should reflect it in the y-axis.
Right.
So it would reflect it in the y-axis and also change the speed of it. Yeah? So, yeah, I'm trying to use my words very carefully here. So this changes the period of the graph. Now, for all these others, the value that we've been finding is actually the A and the B. Okay? But here, what we're finding, the period is not this value. Okay? Because what we have to remember is that the period was originally 360. So what we're doing is trying to compare our original period to our new period, okay? So, for the sine and cosine graphs, the original period is 360, and so for our new graph, it would be 360 divided by whatever number that was, okay? So if we had 3x, so if it was sine 3x, then our original graph period would be 360, our new period would be 120, because that's 360 divided by 3. And that means it's happening faster. Does that make sense? It also means that if we were trying to establish the value of c, if we can see what the period is, we could do 360 divided by our new period. So if we can see that our new period was 120, then we could establish that the value of c was 3 because we could do 360 divided by 120. Yeah? Another way of saying is how many cycles does it do in 360 degrees? So if you look at your 360 degree normal cycle and you identify how many cycles it actually has completed within that time, that will also tell you the value of c. Alright? So there's a few different ways of doing it. For the tan, obviously it's all based on 180 rather than 360, but the same principle applies. So, as I've said here, my original graph is the black one. So what kind of graph is this? Sine, right? So we're looking at sine. We're now trying to establish how many cycles it's actually taken, how many cycles it completes within 360 degrees. So within 360 degrees, I've done 1, 2, 3 cycles, which means that my value of c here will be 3. Okay? So the equation of this graph would be y equals sine 3x. Okay, this next one, oh gosh, it's getting quite long. And again, what kind of graph is the black one? Cosine, yeah. And again, we've got choices here because things are clearly labelled. You can either say how many cycles does it do in 360. So it's 1, 2 cycles. So we know the value of c is 2. Okay. We could have said, right, I can see that my period starts here and goes to here. So my period for this particular graph is 180. So I would do 360 divided by 180. Okay? So there, as I say, there's a few different ways of finding these values. So my equation would be y equals cos 2x. Like